Hello students, so we will be discussing about von Oppenheimer approximation. So in molecular spectra. So it is based upon the following postulates, which says that we cannot classify molecular energy state according to electronic angular momentum. So can't classify molecular energy state according to electronic angular momentum. Which happens to be L. And the reason is that this L is not conserved in molecules. This is one of the postulates. The second postulate is this is we call it, this is number one. The second postulate, number two, is the energy of each vibrational and rotational motions is quantized. Energy of each vibrational and rotational motion is quantized. Which actually leads to the fact that there may be more energy levels in a molecule than in an atom. There may be more energy levels in molecule than in atom. So the second postulate. Now the third postulate is, actually it's not a postulate, it's a way of solving the complete wave equation. And we can do it by considering the electronic wave equation as so this is electronic wave equation. This is the Schrodinger's equation, H Hamiltonian operator acting on the electronic wave function, giving the electronic energy levels as eigenvalues. So this is the operator. Now, having obtained electronic energy level, the nuclear wave equation is nuclear plus electronic wave equation acting on the nuclear wave function, giving you the value of E, the total energy. So let's put this as S dash because it is an operator now. So these energies E, these are the characteristic energies for the whole molecule. Characteristic energies for the whole molecule. Now, we have three types of molecular spectra. Consider molecular spectra. We have three types. The first one is electronic. The second one is vibrational rotational. And the third one is pure rotational. Pure rotational spectra. Now, in the pure rotational spectra, so coming to pure rotational spectra, and they are observed in absorption in the far infrared region. So observed in far IR region, and that is 10 to the power 2 to 10 to the power 3 micrometers. And they are also observed only for heteronuclear diatomic molecules, only in heteronuclear diatomic molecules. By heteronuclear diatomic molecules mean there has to be two atoms, and these two atoms should be different. That means if this is A, this has to be B. It cannot be AA or BB. It has to be A and B, and the number should be always be equal to 2. Okay, cannot be less than 2, more than 2, or less than 2. So this is what we mean by a heteronuclear diatomic molecule, and the pure rotational spectra in this range is only observed in this type of molecules. And another condition for the pure rotational spectra is they should have a permanent electric dipole moment. So should have a permanent electric dipole moment. And can absorb or emit electromagnetic radiation in such transitions. And absorb or emit electromagnetic radiations. Now, the moment of inertia of such a molecule, moment of inertia of a molecule as a rigid rotator. So, considering the molecule as a rigid rotator, the moment of inertia I is equal to mu r square, where mu is the reduced mass, which is that one MA MB divided by MA plus MB, and R happens to be the distance from the axis of rotation. This is the equation for the reduced mass, and the eigenvalues or the energy values for a pure rotational spectra are given as E is equal to, we got it as ER is equal to H cross square by 2I to J into J plus 1, or you can call it as H square divided by 8 pi square I J into J plus 1, where J is the rotational quantum number, and the value of J stands for 0, 1, 2, 3. Now, there is another way of writing the energy. That means if we divide this ER by CH, then we get function of J, which is equal to B into J into J plus 1. This is representing the energy in terms of wave number. So this is in terms of wave number, where B is equal to H by 8 pi square I into C. The wave number is again written as what is represented as nu is equal to 2b J plus 1. So this is the wave number which we get in terms of energy transitions or transition between energy levels. At the value of J as usual is from 1, 2 and 3, whereas the value of this new just stands for 2B, 4B, 6B, etc. for different values of A. So it implies, so if this is the wave, this is the wave number, it actually implies, and the absorption spectrum of rigid rotator should consist of equidistant lines. So the absorption spectrum of rigid rotator, it consists of a series of equidistant lines with a constant separation of 2B, and population in the jth level, population in the jth level corresponding to the lowest level. Is given as this is the population Nj, so Nj by population in the lowest level is equal to 2J plus 1, and here it is exponential minus Ej minus J0 E0 by Kt, and it is also equal to 2J plus 1 exponential minus B J into J plus 1 CH by KT. CH by KT. Now, this is all about Fourier rotational spectra. Now, if we go to the vibrational spectra, so vibrational spectra consists of a series of lines which are actually not equidistant. So a line is missing in the center of the band, and the missing line is also known as the null line or zero gap. So considering the vibrational, considering the vibration rotation spectra, so it consists of it characterizes of a series of lines which are not equidistant, as in the case of pure rotational spectra. And missing line at the center of the band. And that missing line is called a null line or a zero gap. Now, in a harmonic oscillator, so consider a molecule which can be considered as harmonic oscillator. The allowed energy levels are of course H mu oscillation V plus 1 by 2, where V is the vibration quantum number and it is equal to 0, 1, 2, etc. And again in terms of wave number, so if you divide, so let's call it this EV, so if you divide this EV by CH, we get mu oscillation divided by C E plus half, and it is represented by quantity G nu, and in terms of rotational quantum number, it is equal to omega V plus 1 by 2, where this omega is equal to mu oscillation by C, and it is called the vibrational constant. Now, the characteristics of vibrational transitions are they can so vibrational transitions are they can only occur when the molecule has a permanent dipole moment which changes with distance. The conditions are the molecule should have a permanent dipole moment, and it should change with distance. Now the spacing, as we have already discussed, the spacing between the vibrational levels, between the vibrational levels are larger than rotational levels. That means EV is greater than ER, and they are also EV is in fact also larger than KT at room temperature. This is quite expected because the vibrations are governed by temperature. So if you increase the temperature, there has to be more vibrations or vibrations of higher energy. So that actually means that the CV should be greater than KT at room temperature. And another postulate is the vibrational spectrum is expected to consist of single band. Vibrational spectrum consists of a single band and it is omega at centimeter inverse. Now, whatever we have discussed is about considering the molecule as a harmonic oscillator. But in reality, it's not always an harmonic oscillation. There is also, in reality, it is an anharmonic oscillation. So, if you consider it as an anharmonic oscillator, then what are the changes that we can expect? In the harmonic oscillation, we have the selection rule that there should be a change in the vibration quantum number s plus minus 1, but this is not strictly followed in an enharmonic oscillator. Not strictly followed in an enharmonic oscillator. And change in vibration quantum number greater than 1, it actually takes place. This is one of the postulates, one of the differences that we have in an enharmonic oscillator. And the energy level also gets changed. So G mu, initially it was, for harmonic oscillator, it was omega oscillation V plus 1 by 2, but for anharmonic oscillator, an extra term gets introduced, that is omega E xi E V plus half whole square. This term, this is called the anharmonicity constant. So this is anharmonicity constant. Now this anharmonicity constant is always smaller than omega E and always positive. So based upon that, the vibrational frequency of an harmonic oscillator is omega oscillation in terms of V, it is equal to C omega E minus omega E xi E minus 2 omega E xi E into V. And the frequency omega oscillation minus 1 by 2 is equal to C omega E, and omega E is actually it is the vibration frequency that an anharmonic oscillator would have classically for an infinitesimal amplitude, that is an imaginary case, and this V is equal to minus 1 by 2 is very bottom of the potential energy curve. So omega oscillation or new oscillation is equal to omega E is equal to 1 by 2 pi Ke by nu, or Ke is equal to 4 pi square mu C square omega E square. Next is if we have considered a molecule as AB, right? Now if somehow we replace one of the atoms by its isotope, like A dash, which is the isotope. So what changes can we have due to this substitution? So due to this, what will happen is so this is called the isotope effect. So due to the isotope effect, the vibrational levels of the heavier isotope, so heavier isotope have a lower levels. That means G dash nu, the heavier one, should have energy values less than G mu, the non-isotope one.